In this lab, we will be observing the Faraday's law in action. Faraday's law show that how the number of loops in a coil N and magnetic flux change in phi, time change in t, can influence the electromotive force epsilon or induced voltage. Since we'll be using just one coil for the whole experiment, we are only looking at the change in magnetic flux under change in time. Furthermore, we will be observing and recording the magnetic field and electromotive force induced by three different magnets. For the last step, we will be figuring out how to increase the induced voltage by 20% without affecting the intensity of magnetic field.
This picture shows the materials needed for experiment 8, labeled A through H. A is the stand needed to hold up the clamp and the copper coil the magnets will be passing through later on in the experiment. D is the cushion pad the magnets will fall onto in order to prevent their breakage. E are the three different magnets of different sizes, a cylindrical one, a spherical one, and a rectangular one. F is the magnetic field reader, and H is the voltage sensor, both of which are connected to the Capstone 850 universal interface with the Capstone program running on the PC. The voltage sensor is also connected to the copper coils through alligator clips in order to read the voltage.
To begin, we set up the stand and clamp to hold the copper coil steady. Under the coil, we placed a cushion pad so the magnets wouldn't get damaged. We used three magnets of different shapes, a magnetic field reader to measure their field strengths, and a voltage sensor connected to capstone to record the induced EMF. The coil stayed in the same position the entire time, and every magnet was dropped from the same exact height.
Somebody want to work over here with them? So, do you want to try to get a close up with the data?
Do we have to hold it in the air? Can we just like put it on the desk?
Before collecting EMF data, we measured the magnetic field of each magnet. We placed the magnetic field reader directly on the magnet surface and recorded the maximum value. Then we compared each magnet to the base magnet and calculated the percent difference. These values were used later to compare how changes in magnetic field relate to changes in EMF.
In our group chat too. Yeah, it was Dude, you should have seen us like at
To measure the induced EMF, we dropped each magnet through the coil 5 times. For every drop, we recorded the positive voltage spike shown on the capstone graph. After collecting 5 values, we averaged them to get a single EMF value for that magnet. We repeated this process for all three magnets so we could compare the results. For step 3, we had to increase the induced EMF by about 20% without changing the magnetic field strength. To do this, we changed a different variable. For example, increasing the magnet speed by raising the drop height or using a coil with more turns. We repeated the trials until we reached roughly a 20% increase. This part of the experiment helped us see how Faraday's law depends not just on magnetic field, but also on the rate of change of magnetic flux. To summarize, our procedure gave us a controlled and reliable way to test Faraday's law. We measured magnetic fields, collected EMF data, and compared percent changes. Finally, we explored how EMF can increase even when the magnetic fields stay the same. All of these steps helped us to understand the relationship between magnetic flux, time, and induced voltage.
This is data analysis for lab 8. So for our first step, we did have to set up our table 1, and this table 1 is to set up the values for the magnetic field. In the previous slide from procedure, we showed how we connected the coils and then how we used the wand to measure the magnetic field and got the digits read out from Capstone software itself. So for our base, we chose the rectangle magnet, and that magnetic field was negative 1.0671. Continuing with our lab 8, we then had to measure the magnetic field of each magnet. So again, for our base, this is the graph that was created. It is voltage on the y-axis and time on the x-axis. So that way we could get the best results and lower only the magnetic field or see the differences in the magnetic field's magnitude. We had to time the seconds correctly. So we tried to average around 2.5 to 3 seconds per each interval. So that way we could get as close to as possible to just the magnetic change. For our first base, which is the rectangle, we did do 5 trials. The first one was voltage change of 0.3, second one 0.3, third one 0.3, fourth one 0.4, and the fifth one 0.2. So the times do vary. The seconds for the first trial was 1.85, seconds for the second trial was 4.8, seconds for the third trial was 7.8, seconds for the fourth trial was 11.6, and then seconds for the fifth trial 14.6. So we do see that as the seconds change, our voltage does stay the same, and then it changed at the very end. We went ahead and got the samples or the numbers for the voltage, added them up and divided by 5 to get the average of 0.3 voltage for the rectangle magnet. Continuing the second step, this is our chart for our circle magnet. So our circle magnet's values were at 0.85 seconds, voltage of 0.18, at 4.6 seconds, voltage of 0.15, at 7.2 seconds, voltage of 0.20, and then at 9.5 seconds, voltage of 0.09, and then at 11.5 seconds, voltage of 0.18. So those are the 5 values, and you can see we got the top values as they were peaking on the graph. Again, the same graph with the y-axis as voltage and the x-axis as time. We did get the average of the voltage to be 0.16 for our circular graph. Okay, and then this is our third and final chart or graph for our cylinder magnet. The quantities for our cylinder magnet were for the first one 3.4 seconds, voltage of 0.08, 6.4 seconds for the second one at a voltage of 0.12. The third one was 8.75 seconds at a voltage of 0.13. And then the fourth one was 11.15 seconds at a voltage of 0.17. And then at 13.45 seconds, our voltage was 0.11 or 0.011. So we did the same thing of averaging the voltages. We add them all up and divide it by 5. So our average voltage for our cylinder was 0.122. And then using this information, we did go ahead and create our table 2. Okay, continuing data and data analysis, this is our table 2 from our 3 graphs from the previous slides. So table 2 is the results of the EMF induced in the coil for each magnet. Again, for our base, which is our rectangle, the voltage was 0.03. For our sample, the circle was 0.16. For our sample 2, the cylinder was 0.122 voltage. The percent difference, the way we found that was our base, which is a 0.03, our 0.16, a new value, times our 0.03 divided by 0.03, and then that times 100. So we found the difference of 433.3 for our sample 1, which is a circle. And then for our cylinder, we found a percent difference of 306.6 repeating. Continuing with our step 2, we were asked to consider the ratio change. So the ratio change would be the magnetic field over the electromagnetic force. So using the numbers that we had gotten from our table 1 and our table 2 and putting them in that ratio or that fraction, the quantities we would get for our circle, our sample 1 was 1.6. The quantities we got for our cylinder, which is our sample 2, was 0.17. So we do see a very big change. Again, following our experiment, if there was about a 5% change, that's considered neglectable. But the change, the percent differences overall was rather big. But again, the numbers did change drastically as we tested each magnet.
So for the experiment, we were testing how the magnetic field affects the voltage induced in the coil based on Faraday's law. And what we found is that the magnetic field increased, the induced voltage also increased. For example, our circular magnet had the biggest change in magnetic field, and it also gave us the highest voltage. The cylindrical magnet also increased both, but not as much. And even though the voltage increased by a much larger percentage than the magnetic field, they both follow the same trend. And this tells us that it is not just the strength of the magnetic field, but also it's how quickly it changes that affects the voltage. And overall, our results support our prediction and match what Faraday's law explains.